Assalamu alaikum everyone. I hope you guys are doing well, and thank you for coming in. Thank you for joining in, and welcome to another live stream. What we're going to do today is we're going to go over this paper that I just received. This is Feb March 2025. Pretty recent, I guess. It's the most recent paper that we have had. Now the thing is, I would love to go through all of these. Okay. And then if you have any questions, feel free to send them to me. I'm gonna put my WhatsApp number here in the description, so that if you guys need to send me any questions that you want me to solve or to answer, then you are free to send them to me. So the number is in my WhatsApp. Sorry, the WhatsApp number is in the description. So feel free to send any questions that you want over there. So once we're done with this, we're gonna go over it. Alright, so let's get started. As you know, this is the new format. We have 1 hour, 60 minutes, and 60 marks. And they have changed a lot of things here. So let's get started with this question. Okay. Ink contains different colored substances called dyes. Now the thing about dyes is that they are soluble in water usually, which means that once they dissolve, the solution that you see, it is still see-through. You can see it's not entirely opaque. Okay, a student used chromatography to investigate the colored dyes contained in different, the colored group. So this is chromatography. You can see that this is the baseline, and on the baseline basically we put the drops. Now what has this student do? He or she, they have put the dots below it. Now why do we use the baseline? Because what we are trying to do is, this is a starting point, kind of like this is a race between all these different dyes, and we want to see कि वो कितना ऊपर जाएगा, that how far do they go. So right now what they've done is they've put them below the starting point. That is not right. So that's the first error that we have. Similarly, how would they know when to stop? If they just dip this chromatography paper in water, water is going to go and run all the way to the end of the paper. That does not help us in any way, because we cannot use RF value. So they have to draw this solvent front, okay, and that is what they have not drawn. So these are the two errors that we are going to do. Walaikum assalam. So those are the two errors that we are going to do. One is that we have there's the dyes are below the baseline. So again, they've not asked you what they should have done, they're just asking you to identify the error. So that's what we're doing. And second, that they have no solvent front drawn, so they can't calculate or find out RF value. Usually RF ka F chota hota hai, it's small f, but it doesn't matter. Alright, say the name of the equipment used to draw a baseline on chromatography paper. How do you draw the baseline? Okay, so baseline is a straight line, right? So you use a pencil and ruler, or just a half meter rule or something. Make sure it is pencil, not pen, not some other ink. It has to be pencil, because ink will dissolve in water, but pencil will not. Alright, moving on. The student corrects the errors. Okay, the student corrects the errors and identify the ink which can only contain one color dye. So basically what happens in chromatography is that they split up, and what you get is all of these different dots based on what the ink was made from. So this ink is made of only one thing, so it's a pure color, but this is made of two things, this is made of two things, and anything that's on the same level is the same thing. So these are all on the same level. That means yellow ink is present in orange, green and black. That's basically what it means. Okay, so yeah, so which contain only one dye, that is yellow. Now they're saying one of those, so you can also give blue, but it's up to you whether you want to do blue or yellow or both. The mark is just for the for any one. Deduce which ink could be mixed with blue ink to make black ink. So what's the idea? You want to get the blue one and you want to get something else to make the black one. So blue is already there, so blue is in this one and this one, and yellow is there as well, so we will say yellow. Okay, but here's the problem. If I add yellow to green, yellow to blue, this one and this one, do I get black? No. Why? Because I also need this second point. So I need this one as well. So that's why you will not write yellow, you will actually write orange. Okay. So this is a common mistake. Make sure you pay attention to the exact requirements that you have. Okay. Deduce the color of one dye that is contained in all three of the orange, green and black inks. So color of one that is in orange, green and black. So that's definitely yellow. We have already seen that. So that is the answer. Okay. Pretty easy. Okay. All right. If you guys are comfortable or if you have any questions, feel free to ask them anytime. Okay. Yeah. I'm looking at the chat. I'm good. Thank you. Alright, a student investigates the temperature change when copper 2 sulfate reacts separately with two different metals, zinc and iron. Basically, there's many angles that they can take here. They can talk about rate of reaction, they can talk about reactivity series, they can talk about solubility, a lot of things. But what they're doing here is temperature. So that clearly tells me this is rate of reaction. Okay, student does two experiments. Okay, what he's doing. Use a 50 cm cube measuring cylinder. The moment you see measuring cylinder, that means there is an improvement that you can make, that instead of using measuring cylinder, you can use burette. And maybe later on we will see a part where they ask you what improvement you can make. So measuring cylinder can be replaced by a burette, which will give us a much better value. Okay. All right. Sadim, I could not get the O-level paper. I don't have it. If you have it, send it to me. I was just checking Cambridge official website. They only have until November 2024. But the format is pretty same and the questions are also very similar. Alright. To pour 30 cm cube of copper 2 sulfate. Again, the same idea. Out of 50, he's pouring 30. There's going to be some error there which can be improved if he used burette. Copper 2 sulfate into 100 cm cube beaker. So, uske paas kya tha? He had this 100 cm cube beaker. He used a magic cylinder and right now we have 30 cm cube of copper 2 sulfate in this. Okay, so that's what we have here. Alright, using the thermometer to measure the temperature of the contents. Why are they doing that? Because they want to know the room temperature. This is the starting temperature. That is what they're doing. So room temperature is important because we want to know where we start. Alright, this is a temperature at time 0, of course. Add 3 grams of zinc powder to the beaker. At the same time, start a stopwatch. So they're adding 3 grams. Remember, 3 grams is a pretty small value. So you have to be sure that when you're adding it, you measured it right. So they will obviously need the balance. Usually we use an electronic balance for such small values. So electronic balance, and he's also adding stopwatch. Kind of difficult to do and to time it, but again, that's again a source of error. Okay, using the thermometer, continually stir the mixture in the beaker. Okay, so he's stirring it. There's a thermometer here. All right. Measure the temperature of the mixture every 30 seconds for 10 seconds. So he's measuring two things. There's the time, which is in seconds. You can see over here. Okay. He's starting at 0. He's going all the way to 210. So 30, 60, all of those. And then he will obviously measure the temperature, which is probably in degrees Celsius. And that also tells me that this is the two variables. If you think about independent and dependent variable, the independent variable is time. Once he starts, that is going to determine how long the experiment goes, and temperature is basically the dependent variable, which is the value that he gets. Now this temperature will obviously rise from room temperature, which we already have, and it will eventually, once the experiment is done, it will start to fall down. So there's going to be an increase and there's going to be a decrease. Probably they'll ask you to draw a curve. Probably they'll ask you to draw two lines, one for increasing, one for decreasing, and wherever they meet, that is the maximum point. Okay, so just by reading this, we have all these different ideas coming to our heads. Alright, repeat experiment 1 using 3 grams of iron. So this was with zinc, they will do the same thing with iron, and they will get all these different values. Okay. Alright, so this one's pretty straightforward. You just have to get the values. So this one, again, make sure that you first read the scale. Is it going from top to bottom or bottom to up? Usually, everything goes from bottom to up, except for burette, which you read top to bottom. Okay, so just make sure you understand how the scale is. Okay, so this is going up. So this is 30, I get 33.5. Again, even if you want to write 33, write 33.0. And obviously, if you are writing 0.0, you have to be sure that it's exactly 33. Okay, this one is, I guess, 38.0. This one is 41.5. This is 43.0. and this one is okay, this is going to take a long time. I wish I had the mark scheme for this. 44.0, 43.0, 42.0. Okay, so temperature change is basically that you're subtracting this value, and because they're saying since time is equal to 0, you're subtracting 24 from every one of them. So it's 8.5. This is, I guess, 38 minus 24. What is it? 14.0. Okay, I'm just gonna pick that calculator, whatever. Okay, so 41.5 minus 24. So 17.5, and this one is 19.5, and this one is 44 minus 24, 20, and this one is 19, and this one is 18. Okay, so you can clearly see the temperature is falling as well. Alright, this one 24.0, 21, 25.5, this one is 28.0, 28.0. Wow, same values. And this one's also 29. What's happening here? The rate is the temperature is increasing very slowly, and it's also changing very, very slowly. That's what's happening here. Okay, again we subtract them. So 2.0, 3.5, and 6.0, 6.0, 6.0, 7.0, 7.0. Okay, so that's how this is happening. So what this is telling me is that even after all this time has passed, it has not started to decrease, which means that maybe they have reached the maximum value, which you can clearly see that this is repeating. So either the rate of reaction is really slow, or this is the maximum value that you get. Okay, all right. Complete a suitable scale on the y-axis. So again, how do you know the y-axis scale? You look at your values. What are we drawing? We're temperature change. Okay, so temperature change means I'm gonna look at from 0 to the highest value, which is 20. So I need to make sure that 0 to 20 fixes in there. So I'm just gonna go with 5. So 5, 10, 15, 20. Okay, I could pick another scale like 4, but I don't want to do that because then 2.5 and 5, I mean I could do that, doesn't really bother me that much. So 4, 8, 12, 16, 20. What do you think is a better choice? Turns out both of these are okay. Alright, but if it was like 3, 6, 9, I will never do that. For now, we are trying to use the maximum area that you have. So I'm good with both of them. Okay, so what are we going to do next? Draw two curves of best fit. So curves, which means that one for experiment 1 and one for experiment 2. We already have a point. Okay, so let me just write the values here somewhere so I can easily draw them. I'll just take a screenshot. Okay, where did it go? Alright, so I have the values here. Okay, so we're starting with 8.5. So at time is equal to 33.5, which is a little hard. Time is, wait a minute, that's time? Let me see. No, time is 30, 60, 90. Okay, so at time is equal to 30, which is gonna be here. This is 8.5, so that's definitely this one. Okay, and then 14 at 60, so 60 is here, and what is it, 14.0? So it will require some effort, but that's okay. Good thing. 17.5 at 90, so 17.5. This is 17.5. Okay. 19.5 at 120. So 19.5 over here. And 20 at what? 20 at 150. So 20 at 150. And then 19 again at 180. And then 18 again at 210. So 18 at 210, which is probably here. Okay, so this is one curve. Okay, So I'm just gonna draw a smooth curve here. Make sure that once you draw it, you connect all the points. And there you see a problem with going all the way to the top, because then it is difficult to include this point. You might go outside the curve. So you have to be very careful when you're drawing it. Unfortunately, I couldn't connect all of them with a smooth curve. But that's okay. I mean, if you were drawing them in the exam, you would be expected to join all the points, and it might take you a while to get that. Okay, I'm just gonna go with this one. All right, we have the other one, which is starting at 30. It is 2. Okay, so this is 4, so this should be. Oh, wait a minute, my scale is wrong. Is it? Yeah. Am I doing it right? No, I am doing it right. This is 2.5 for 1. Oh yeah, so this is going to be a hassle. I'm gonna start over because this is going to be 2.5 for 1 is a difficult scale to pick. I'm just going to go with 5, 10, 15 and 20, assuming that I get something like this. Okay, so just gonna go something like this, and for the other one I'm gonna go and pick something that goes like, it's gonna go something like this. Okay, so that's how it goes roughly. Again, I'm not drawing them yet, saving time. Okay, extrapolate the curves on your graph to deduce the temperature change since time 0 after 240 seconds. So extrapolate means you continue them the way they're going and then see where it will go. So this one I'm going to continue, and this will probably go here based on how it's going, like this, and this one probably going like this. Okay, so I extrapolated it for 240, so I've actually gone beyond that, but that's good. Okay, so okay, so experiment 1 is this one. At 240 I will have this. Okay, so I have to draw the line on that to figure out what the temperature change is. So that's gonna be this one. Okay, so again, this is my value, which is gonna be, I guess, what is it, 13. Okay, so 13 degrees Celsius, that is my change. That's the one I'm gonna go with. State which experiment 1 or experiment 2 is the more exothermic one. Clearly we are seeing that experiment 1 has higher difference, higher change. So we're going to go with experiment 1, and that is greater temperature change. Okay. A question is, can line of best fit be a curve? No, line means line. Even though mathematically it's a curve, but in chemistry line means line. Okay, so if they ask you for line of best fit, as Janvi has said, you can draw that and you don't have to connect all the points. Okay, yeah, okay. Graph is difficult. Graph के ऊपर time लगाएं, takes a while, you need practice. Something's wrong with the connection here. My screens keep turning off. Okay. If they wash the conical flask with water in titration, does it affect the readings? Yes, because if you wash it with the conical flask with water, you're going to end up with some drops of water in there, changing the concentration of what you have and the volume of what you have. So both of those will affect your rate of reaction, and you might need more acid or more alkali to neutralize it, which obviously affects it. Okay, so we usually wash it with the solvent that we have, because that way we ensure that one, we don't have to have we don't change the concentration, and secondly, the solvent volume gets added to the total volume that you have and doesn't change that much. Okay, all right, Musa and Shaky, relax. Okay, predict the temperature of the solution of experiment after 1 hour. After 3 hours. 3 hours is one. Wait a minute. After 3 hours, it will go back to the room temperature. So room temperature was 24, so it's gonna come back to 24. Okay. Explain why using a copper container instead of beaker would not be an improvement. Okay, so copper container instead of a beaker would not be an improvement because copper will lose out. It's a conductor, right? So it's going to increase the rate at which we lose the heat, or it is going to increase the speed with which heat is lost, or it will going to increase the heat loss. So copper is conductor, so heat loss will increase. Okay, second reason is that copper is opaque. We will not be able to see whether it has dissolved or not. It is opaque. That's also another option, so we can't see how much solid has dissolved or not. Okay, so clearly both of those are useless changes to make. Okay, describe two changes to the apparatus so that will improve the results of this investigation. First one is that use burette instead of meshing cylinder. And what's the reason for that? Very simple. Burette has higher precision, so less error in volume. Again, examiner doesn't expect a lot of detail, but this is good enough. Second, change 2. Notice that for experiment 2, this is very slow. So we might want to do it for longer period of time. So do it for more time, especially for experiment 2, right? And that is, explanation is that rate of reaction for, again, I'm writing Rx, but don't write that in your exam. For experiment 2 is slow, so give it more time, or to more time will, so more time allows better tracking. You can also say that repeat the experiment and average out the values. That's also something you can say. As on test 2 substances, solution A and solution B. Wait a minute, I'm gonna just look at your answers. Why do we wash the rest tube before experiment? Obviously we want to make sure there's no impurity, and secondly we want to make sure that once you have passed it with distilled water, that water is not there. You have to wash it with the solution so that the concentration of the solution doesn't change. We asked the same question in the MS. It was no change in concentration basically. For conical flask, it doesn't matter. Well, it does matter, but not that much, to be honest, because the volume is going to be really, really low. But burette, it definitely matters a lot. Okay. Solution A is aqueous chromium 3 chloride. Foreign आपके ज़हन में colors आने चाहिए. You must know that it's chloride. So silver ion will react with it. This is chromium 3, so makes green solution. Green PVT which dissolves in sodium hydroxide. And how do you know? Very simple. You remember crazy cousin? So crazy cousin. So these are the ones that dissolve. So chromium, aluminum, zinc dissolve in sodium hydroxide, and copper and zinc dissolve in ammonium hydroxide. So chromium is the one that's going to dissolve in sodium hydroxide. Green PVT dissolves, and later on green PVT stays because chromium is not in the cousin, right? So crazy cousin is a way to remember that. Although you don't need to remember, you have the notes, but it will just save you some time. Okay. Chaining the apparatus here can also be a change that you can do, because it will make sure that you are done. You don't have, like the burette or all that, whatever you're using, it's not contaminated with what was there before, but again, not that required. Okay. Insulate the beaker to avoid the heat loss, but definitely a very good answer. Take a lid, add some lagging, all of those perfect answers. Okay. Use the cotton to reduce heat loss, perfect answer, very good answer. Yeah. Okay. To the first portion of solution A, this ab wo kar kya raha hai? What he's done is that he has 3 portions of solution A. So there's chromium chloride here, chromium chloride here, chromium chloride here. Okay, to the first portion of solution A, this one, student adds aqueous sodium hydroxide dropwise until it's in excess. So what are we gonna do? Chromium, green precipitate, and dissolves in excess. Okay. To the second part, this one. Uh, he adds nitric acid followed by barium nitrate. Barium, this is chloride. Barium chloride is soluble, right? Barium is only insoluble with sulfate, right? And other things, but we use it to test for sulfate, right? So because of that, we can easily say that this will be no change, or even if it dissolves, if it makes white powder, it's going to be soluble, so it doesn't matter much. So we'll just say no change. Okay. To the third portion, he adds nitric acid followed by silver nitrate. So in this one, so the moment he adds it, what are we going to get? We're going to get white precipitate of what is it? Silver chloride. So white precipitate. Okay, that's what we're gonna get. Okay. All right. Carry out a flame test on solid B. So this is what they're doing. They're doing all these tests, and then they're going to ask you to check the colors. I don't remember these colors by heart, so I'm just gonna get the notes that you have. So where is it? Yeah, found it. Okay. So while you're just reading it, don't just rush to the question. When you're doing it, write down whatever you think it should be. So this is gonna be lithium, because lithium ion gives me red color. Okay. Dissolve the remaining solid in distilled water to form solution B. So you have solution B divided into 3 parts. So this is B, this is B, this is B. Okay. All right. And that probably has lithium in it, but other things could be there as well. Okay. To the first portion, add a few drops of acidified potassium manganate 7 pale purple solution. So that means it does not react with it. It is not an reducing agent, because KMnO4 is purple itself. So you have added it, obviously it's purple. There's no change. Okay. Okay. Solution remains colorless. What have we done? We have added sodium hydroxide. That means it doesn't produce any precipitate. So it could be group 1 most likely. But again, we don't know. Warm the product of test 3. So this one that you have in test 3, what do you have? You have sodium hydroxide, remember, and you have that solution, whatever it was. Okay. Test any given gas off with damp red litmus paper. It remains red. That means no ammonia. Okay. If it is giving a gas, that gas is acidic, but that's it. We don't know if the gas is given or not. So you've added sodium hydroxide, heated it, and you still didn't get any blue precipitate, that red litmus turning blue. That means it's not ammonia. So there's no ammonium ion in there. To the third portion, I add about 1 centimeter cube of nitric acid followed by barium nitrate, very white precipitate. That is sulfate ion, definitely. And so let's move on. Describe how to carry out the flame test used in test 1. So how do you do this flame test? So the way to do the flame test is you take a small portion of it in what you call like it's a small tube kind of thing. What is it exactly called? Let's see. Okay, so it doesn't say what it's called, but what you can do is you can take a wire, okay, and just make a loop of the wire and add a small piece of that salt onto that, dip it in the sample that you have. So let's say this was a sample. So I'll take the small wire with the small loop at the end, dip it in there, okay. So the solid, obviously some part of it will be there, and then put it on the flame. And once the change in the flame is seen, you just note it down. That's all you do. Okay, so you can take a nichrome wire. Why nichrome? Usually we take nichrome, but it doesn't have to be nichrome. Nichrome wire. Nichrome has a high resistance, so that's why we use it. Okay, it doesn't melt that easily. It doesn't heat up that. I mean, when you're holding it, of course you have to wear gloves and everything. Okay, so take a nichrome wire and dip one end in the salt. Put that end, not the other one, on flame and note the color change. Okay, right. Now you'll notice that this is very different from how the mark scheme says it. Mark scheme has different words. I haven't seen the mark scheme for this one yet, But that doesn't matter. The point is that whatever you're doing, you have to make practical sense for that, and should show that you understand how it's done in the lab, whether you're doing it in the lab or not. Identify the ion that is tested in test 4. Test 4. What ion are we testing for? Again, not to say that we found that. Okay? What are we testing? You have sodium hydroxide and you heat it up. What ion gives you a gas with sodium hydroxide and heat? Obviously, we add a little bit of aluminum in there as well. But you can simply say, because you did not add aluminum, you can say ammonium ion is the one that you're testing. With nitrate, you have to add aluminum foil so that you get sodium hydroxide, ammonium foil, and then you test it. So clearly, we did not add any aluminum, so ammonium is the one that we're testing for. Identify the two ions which are in solid B. So there's lithium ion because of the flame test and sulfate ion because of the barium precipitate. Okay, and that's it. We're done with this part. Any questions? Let me see. So there is some improvements on my answer. So somebody's saying platinum wire, definitely take that. Yes. I don't understand what non-luminous blue flame would be. I really don't understand that. But it's okay. Maybe you do. Okay. Dip in HCl first to remove contamination. Sure. If there is any other powder there already from the previous test and all that, it will react with it. Sure. That's a good idea. But I don't think it's required here. But you can write it. Okay. All right. What's the handwriting? I'm sorry, handwriting maybe Achini. I'm really sorry. Okay. All right. Sarim, I'm not sure when I will end my teaching break. Honestly, I don't know. But abhigili, I'm not changing my mind. We'll see. We'll see. All right. Metal spoons can be electroplated with silver. Okay. Describe how a metal spoon can be electroplated with silver. So you have silver, you have the metal spoon that you're plating. Now silver makes positive ion. That means we want this to be the cathode and this to be the anode. Include in your answer how you could determine the mass of the silver electroplated on the metal spoon. So how would you do it? You'd measure the spoon before you start the process and you measure the spoon after you end the process. Okay. Yes, this is March 2025. Okay. You're provided with solid silver nitrate. That is the electrolyte that we're going to have. Metal spoon, that is the anode. Sorry, not anode, cathode, sorry, my bad. I've already wrote it, but then, okay. So cathode, this is going to be anode, and distilled water and all of that. So distilled water is to basically increase the quantity of the solution. So again, when you say you must include a diagram, obviously you must, but if they say you may, you still must. Okay, always draw a diagram if you can. Alright, so I'm gonna just draw a random thing. This is going to be silver nitrate solution. This is aqueous, just to show that it dissolves. I'm gonna have a cathode and I'm gonna have the anode. Okay, so this is the spoon that I have. Alright, there's going to be obviously battery here. Alright, so let's see. Have I connected the battery correctly? What do you guys think? No. Why? Because what's happening here is that this is positive, this is negative, and this one is positive. No cation is going to come here. So that's why make sure that your polarity is correct. So it should be the other way around. Now it's good. Alright, so this is going to be, always label your diagram. So this is going to be silver. Okay, this is going to be metal spoon. We don't know what metal it is, but it doesn't matter. And the setup is complete. You can include a bulb if you want, just to see if it's running or not. Again, your choice. Okay. Usually when it's done in the lab or in the industry, they just time it and they know how long it takes. But yeah, including a bulb is a good choice. You can add it if you want. All right. So now here's what you're gonna do. I write in steps. I try to write in points, but again, it's your choice. If you want to write in paragraph, that's perfectly fine. Okay. So I'm gonna do that. Measure the mass of metal spoon and record it. Again, I did not mention how you're going to measure, right? And that's fine. You don't need to include electronic balance because that's pretty straightforward, but if you want to, that's okay. And you can see my dog. It's actually my friend's dog, but you can see it over there. Okay. All right. Next one. second thing is, once you have the mass, now set up as in the diagram and turn the switch on, turn the solution, turn the thing on. No, I'm not in New York, I'm in Boston. Okay. Turn the switch on. Okay. Run it for as long as you want, sure. Run it. Okay. Once completed, or once the change is seen, or once the silver is plated, okay, stop or turn it off. I mean, it's pretty straightforward. So turn off and measure and record mass of spoon. And I'm gonna write an equation here. The mass of silver equals spoon final mass minus spoon's initial mass. Again, I'm not making a lot of sense. It's not very neat, but it's perfectly fine. For the examiner, it's good. Okay, let's see if we have missed anything. What have we done so far? Have we described how it can be electroplated? And have we done the setup? Yes, perfect. We have shown the silver here, we have shown the spoon should be here, we have corrected the polarity, we have shown what the solution is going to be, and we have shown that how to use water, which is the solution is aqueous. Second, determine the mass of electroplated. Have we done that? Yes, we have determined the final, the initial, and the mass of silver that is plated. And yeah, we are done. This is a boxer. He's just sleeping, I guess. Okay, he's just resting. Yeah. Salim, I'm traveling. I usually live in DC, Washington DC, you know. Yes, he's a very cute dog. Alright. Oh wow, this was a short paper. Okay, so we are done. Alright. I am going to take your questions now, and then we are gonna see. Yes, he's a boxer. Okay, so I have received winter 2024 paper for O levels. Let's see. But before that, I'm gonna look at the questions here. Okay, so here's the question. C1 V1 over N1 N2. So this question, this formula, C1 V1 over N1 is equal to C2 V2 over N2. This is called titration formula. Okay, this formula can be used in O levels because I have not seen in O level marking. Of course you can use it on O levels. It's perfectly fine. You can use it in O levels, you can use it in IGCSE, you can use it in A levels. There's no problem with that. Yes, you can. Okay. Alright, so I'm gonna do O levels winter 24 paper next. Okay, after this one. But let me just take the questions. Okay, so first question is why acid does not display its property in precipitation reaction, and what is meant by that? Very good question. Okay, so let me just type it out. Okay, so the first question that I have here is that why acid does not display its properties in precipitation reaction? Because precipitation reaction is ionic precipitation reaction, it's not acid reaction. Acid works as an acid when it gives a proton. In precipitation reaction, that's not what's happening. In precipitation reaction, one ion is being exchanged by another ion. Let me give an example. Let's say I have HCl and I react it with sodium. What's going to happen here? HCl is going to lose the proton, and that proton is going to go and make hydrogen gas. This is a redox reaction, but it's also losing the proton. Okay, and sodium is going to obviously lose the electron and become sodium chloride here. Okay, so this is an acid, characteristic acid reaction. It lost proton. Okay, so what's acid? Something that loses proton. Does it do that here? Yes, it did. So yeah, definitely. HCl reacting with sodium hydroxide. What is happening here? Sodium hydroxide is ionized. HCl is ionized. Sodium is going to react with chloride, but that's not the main reaction. The main reaction is this proton is going to react with this hydroxide. So H plus and OH minus, they react, make water, neutralization reaction. And then whatever is left, that is the spectator ion. So they just do that. Okay. Again, this is an acid reaction. This shows that HCl is acid. Similarly, HCl plus sodium carbonate, for example. Again, carbonate is going to break down, give me carbon dioxide, and that oxide, the one that's left over, that is going to react with hydrogen and make water. Again, what's happening here is it's losing the proton, that's accepting the proton, acting as a base. So acid की definition पे पूरा उतर रहा है वो. Alright, so there you go. So you get NaCl here. I have to balance it out, and you're done. So this also, all three of them show that HCl is acid. Now let me do another reaction. HCl reacting with sodium nitrate or sodium. In fact, let me make it simpler. Silver chloride, silver nitrate. Okay. What's gonna happen here? Silver is gonna go and react with chloride, make solid. This is a precipitate, right? And then HNO3 are left over, they just bond with each other. This is not an acid-base reaction. This is not an acid-metal reaction. This is HCl acting as one salt, silver nitrate acting as another salt, making a precipitate. The real reaction is happening between silver and chloride ions. It's not the hydrogen that's doing the main reaction. Okay, that is just the spectator ion. So this shows that HCl, it doesn't show whether it's acid or not. This is where it shows that it's acid. Okay. All right. Next question is, why do we wash the residue with distilled water? Why do we wash the residue with distilled water? So that we make sure, where does the residue come from? Residue may have some salt that is still there, that is not dissolved. And if you were to dry that salt, obviously dry that residue, that will mix with whatever you were going for. So let's say I do an experiment and I want to collect sand from salt, right? The simplest example. Or let's just take this example. I have silver chloride and I have HNO3. Let's suppose when I do this reaction, some parts of silver nitrate are left over in the filtration part. What do I want here? I want just silver chloride. I don't want anything else. But maybe some parts of this are still left over. So I will wash it with water so that if there is still left over, they just pass through. That's the concept. That's the reason we always wash the residue with distilled water, so that if there's anything left over, it dissolves and then it goes away. All right, next question. Why distilled water and acid are used in titration? Okay, again, if you have distilled water, then that is supposed to dissolve everything else that you have. Again, why is this creating an issue? I'm sorry, the screen keeps freezing for some reason. Okay, why distilled water and acid are used during titration without removing? I don't understand that question, to be honest. Okay, next part. Why do we warm some solutions while making soluble salts? Some salts, when you make them, the rate of reaction is really slow. So you just heat them up so the reaction is faster and you save time. That's it. Okay. What are observation if something is in excess and if reaction has ended? Again, you always have to look at the change that's happening. If a gas is coming out, then bubbles are going to come out. And if the bubbles stop, reaction stop. If a mass is dissolving and you see that it is gone, all of it is dissolved, that's an observation. That shows that it is, the reaction is done and this is your observation. Okay. Sometimes we have gases coming out, but we don't want to, we want a better way to figure it out. So then we use a balance, because what happens is that if you have a balance and you have a reaction going on, which releases all these bubbles, then the mass reading will drop. Okay. So the mass decreases, and as the mass decreases, you can see that the reaction is going on. And once the mass stops, there's a constant mass reaction that has completed. Okay. Similarly, if you have a gas coming out, let's suppose I have a conical flask and we have a gas coming out, then that can be connected and collected in a gas syringe. Okay, always seal it. Okay, so this is giving bubbles, but then this gas syringe is going to obviously collect the gas. And so we can see that once there's no more bubbles, or this is not increasing or it's not going back anymore, there's no more gas coming out, that's also an observation. Now whenever you're drawing this, make sure you draw these things. These are called graduations. If you don't draw graduations, that means you cannot measure the value, you can only collect it. Okay, so whenever you are going to measure something, you need to draw graduations. Similarly, if you're doing burette, okay, if you ever draw burette, although you usually don't have to, then there's a tab there, and always draw these graduations because we want to see what's happening. Imaging cylinder, if you ever have to draw it, always draw these graduations. Don't spend too much time drawing it. It's always sketching so that you save time and you just get the idea across. Okay. Next question is flame test. So I've already talked about it. All right. Let's look at other questions. Okay. हाँ आपने पहले पता कर लिया था. Okay. Set up the apparatus. Always set up the apparatus. Of course, you should, and you should always label it. Okay. Do we have to name each apparatus and used? Not all of them, to be honest, because if you're drawing it out, जैसे आपने ये diagram देखिए, I've only shown the important bits that are relevant to my result. You don't have to label everything, but if you do, that's up to you. Okay? Yeah. Yeah, I'm sorry, my fire alarm keeps beeping. Okay, any questions? Hermes is saying that you struggle with the electrolysis. Again, this is the extent of electrolysis question that you're gonna get. If you want to look at the detail of that, go to my live stream for paper 2, and I explain at the end of it how electrolysis is, like how do you solve the question. So if there is a question on electrolysis which is about which metal gets discharged and it doesn't, go to my last live stream for paper 2 and theory paper, and you will get it. Okay. All right, so that is done. Let's do another paper and then we will end this session. All right, let me get the paper. Okay. So I'm gonna do winter 24 O levels paper 4-2. Okay. Alright, so this is the paper that you have. यहाँ भी खोल लेता हूँ. Wow, you're from Chakwal, okay. I've been there. वहाँ पे वो पहलवान की रोड़ियाँ होती हैं. एक दफ़ा मैंने यहाँ अमेरिका में मंगवाई थी. Okay, खुल क्यों नहीं रहा है? Sorry guys, just a minute. Alright, I think we're ready. Let's start the next paper. In case you get any questions again, feel free to send them to me. You have my WhatsApp in the description, you can send the questions there. Alright, a student does an experiment to make pure hydrated copper 2 sulfate crystal. Okay, so he's getting copper 2 sulfate. What does this dot mean? It means that it's loosely bonded, and if you heat it up, this water will go away. This is water of crystallization. This is the water that gives us the color blue for copper 2 sulfate. If you lose this, you get anhydrated or anhydrous copper sulfate, which is not going to be crystal, it's just powders. And secondly, it's going to be white in color. So this is used as a test for water. If you ever have to test for water, then you can just use copper sulfate anhydrous, which goes blue when you add water to that. Okay. Alright. This one makes copper sulfate by reacting dilute acid with aqueous copper 2 oxide. Again, you get the cation from copper 2 oxide. So the anion will come from something with sulfate, right? And which acid has sulfate? Sulfuric acid. So I will write sulfuric acid. Now make sure that you name it. You don't write the formula. because the examiner asked you specifically to write the name. Okay. Shows the apparatus the student uses to crystallize copper 2 sulfate. Okay, what's he doing? He's heating it up, giving it a water bath kind of thing. Okay, this water is going to heat up, it's going to release that heat again, and then that heat is going to go. The advantage of this is that water absorbs that heat and then it transfers it much more uniformly than this thing. The disadvantage is it's really slow process. Okay, name apparatus X. What is apparatus X? Sorry guys, I have to take this. I'll be back. Let's resume and thank you so much for waiting. Can I change the color theme? Do you want it to be like light? What do you mean by color theme? Okay. So name apparatus X, that is going to be evaporating dish or evaporating basin. Okay, so that's what it is. Alright, moving on. Describe how the student decides when to stop heating the aqueous copper 2 sulfate. How do you know whether you're done? The result is pretty straightforward. How do you know? The water basically heats up, okay, and you see these crystals that are left over. So water is gone, not completely, but you have these crystals that keep coming up, and so you write that he knows when to stop when there is when he sees crystals being made or crystals being visible. Okay, all right. Suggest why apparatus X is heated with a water bath and not directly. So what do we want? We want to make sure that he creates crystals. We don't want it to heat up all the water, right? So a slower, smoother heating process is better because we want to make sure that the water crystallization stays, it doesn't go away. So with water bath you have a very slow, gentle heating process, so that's why we use it. So water bath provides slow or smooth or gentle heating process, ensuring water of crystallization doesn't escape or stays. Okay, okay, that's what we have. And this is 2 marks. Okay, we're done. 2 reasons are good enough. All right, describe the final step needed to produce pure hydrated. So once you have done heated the when you are done with heating, what's next? You dry it. Okay, and so we dry the crystals. That's the next step. Okay, any questions so far? Okay, a student titrates 4 samples of aqueous sodium carbonate, okay, with HCl. So we have 4 samples, all of them with sodium carbonate, different of those, but we have HCl in added to each one of them. In titration 1, the student rinses and fills a burette with HCl. Okay, burette is a good choice. We don't need to change it. Adds 25 cm cube using a pipette. It's a fixed value, right? So we will use a pipette for that. I mean pipette or pipette. I don't know if there's 2 P's or 2 T's. I don't know. Okay, adds methyl orange indicator to the conical flask. Methyl orange colors are, it goes orange. Oh, sorry, it goes red to yellow, right? It's red in acid and yellow in alkali. Okay. So what's gonna happen? Because in the beaker or whatever you have, what do you have? Conical flask or beaker? They haven't told us. So sodium carbonate is alkali, so it's gonna be yellow, and then as you add the acid, it's gonna turn red eventually when the equivalence point hits. Okay. Add HCl from burette while swirling the flask. Why is it swirling important? Because you need to make sure that it mixes thoroughly. Adding drop by drop near the end point. Again, it's important that one extra drop can change the whole process, and the end point is reached very quickly. So that's why you have to be careful when you're nearing the end point. How do you know you're nearing the end point? When you start, you do a rough titration and you see where the color change happens. So let's say I do it and I see that after adding 17 cm cube, it has changed its color. So now next time when I do it, I have to be very careful right after maybe 14 cm cube. After 14, I'll do drop by drop. Okay, so that's what we do. So rough titration, we don't consider those results, but that is used to figure out where the endpoint is. And then we reach the endpoint more carefully from the next ones. Okay. Okay, the student repeats the titration 3 more times. Why is he repeating? So that he can take an average, reduce his error. Good step here. Okay, shows the burette readings for the first 2 titrations. Okay, what are the burette readings? Over here, again, notice that it is increasing from top to bottom. So bottom to up or top to bottom, you have to be careful whenever you're reading. So this is top to bottom, so this is going to be 21.2. That is the starting value, so 21.2. And the ending value is 41.7. Okay, so 41.7. So I'll just subtract them, so I guess 20.5. Let me confirm. Yeah, 20.5. Okay, next one is starting at 0, but don't write 0, write 0.0, because everything is to 1 decimal place. Write all your values to 1 decimal place. Okay, and this one is 19.9, so 19.9, and so the difference is 19.9. Okay, best titration results are the ones that are very close to each other and preferably lower on the lower side. Okay, so yeah, so the ones that are closest to each other. The difference between these is 0.6, the difference between these is 0.4, so I'm gonna pick these two. Okay, even though 19.9 is lower, it's still much farther away, so I will not consider that. That's not my best result. Okay, so the average is going to be 20.5 plus 20.9 over 2, so that's gonna be 20.7, I think. Yeah, 20.7, sorry. Okay, so that's my value for HCl. Okay, so I need 20.7 HCl to react with 25 cm cube of sodium carbonate. That's what's happening here. Okay, use your answer to calculate the number of moles of HCl in the average volume. Okay, what's the concentration of HCl? Now, here's one thing that I do. Whenever I'm doing it in the exam, I write just small things on the side. So sodium carbonate, okay, and I'll write three things here: CVN. Okay, so concentration of HCl is 0.5, right? Yeah, 0.5. Volume is 20.7. I just found out. Volume for this is 25.0. We don't know the concentration of that, but making this small table on the side helps me understand what I'm doing or keep track of all the values that I need. Okay, so use your answer to calculate the number of moles of HCl. I have the concentration, which is this one. I have the volume, and it's going to be pretty straightforward. N equals to CV. You don't get any marks for writing the formula, but I still write the formula. Again, my choice. You can write or not, up to you. 20.7 is in cm cube. That is in 0.5 moles per dm cube. So I'll divide it by 1000, multiply by 0.5, and that will give me my value. So 10.0.103. I'm just gonna do it. Yeah, 0.01035. Okay. I mean, it's okay. You can write it. You don't have to round it off. It's completely your choice. Okay. You can make it 0.0104, up to you. No worries. Whether you round off or not, no worries. Okay. The equation for the reaction between these is shown. So this I have found out, 0.01035. Now, sodium carbonate is gonna be half of it, right? Why? Because for every 2 you need one of that, so it's gonna be half of that. So 0.01035 divided by 2. So 0.0 whatever that is. My math is not that good. 0.00518. Okay, so that is what I'll write. Okay, done. So that is, no wait, this is not moles. This is moles. I want to find concentration. So this is moles. So I have 0.00518 moles. Now I need to write concentration. So concentration is number of moles over volume. So 0.00518 over 25 divided by 1000, because 25 cm cube, right? So divided by 0.025. So I am getting 0.207 moles per dm cube. Okay. A student is provided with 150 cm cube of sodium carbonate. Use your answer to calculate the mass in 150 cm cube. Again, what do you have? You have concentration, and you want to find mass, but you also know volume. So you have concentration, which is 0.207. You have volume, which is 150. So that will give you moles, right? So number of moles is 150 over 1000 times 0.207. So this is cm cube. This is in moles per dm cube. So units are important. Okay, so I do that. So I get 0.00207 moles. So the mass is gonna be, you just obviously multiplied by mr. Okay, so the mr of this thing is gonna be, sodium is 23. I should write it somewhere. So mr is 2 times 23 plus 12 plus 3 times 16. So that's gonna be 106. Okay, so 106 is the mr, relative mass, or molar mass. So 0.00207 times 106, which will give me the mass 0.219 grams. It's very difficult to exactly get 0.219 grams, but it's okay. We can still find it to what the answer is going to be. Okay, it's very difficult to measure it in that detail, but again, what does it matter? State why the conical flask is swirled while HCl is added. To make sure everything reacts slowly and gradually, instead of everything just piling up at the end. Okay, so we have so HCl is added, so to mix thoroughly. Okay, state why the HCl is added drop by drop, so that we don't add extra acid. when we are at the endpoint. Okay, so to ensure extra HCl is not added after endpoint. Okay, and we are good. Okay, so investigate solution P and solution Q. अब हमारे पास दो different चीजें आ गई हैं. Describe how to do a flame test. Notice that they asked the flame test in November, they asked the flame test in March. Why are they doing that? Because this is something that is usually not taught, even though flame test has been in the syllabus for 3 years now. Usually not taught, so that's why they're doing it. Alright, describe how to do a flame test. So again, as I told you, you take the wire, you dip it, usually a nichrome wire, but it doesn't matter. You put it in the non-luminous. So somebody said non-luminous, right? So put it in the non-luminous part. Usually we put it where the where the fire is fully oxygenated. That's basically the idea. And I think that's what they meant when they say non-luminous. Probably the top part, the blue part, probably that's what they're talking about. So we take the wire and dip in salt. Which salt? P. Salt solution, sorry, it's not salt, it's salt solution. Okay, so solution P, then put in non-luminous part. That I learned something today. Non-luminous part of flame, and note the color. Okay, and yeah, and record the color change. Okay, all right. Solution P contains an anion comprising of nitrogen oxygen. Could be nitrite, could be nitrate, I don't know. Describe a test to identify the anion. Again, we only know about nitrate and its test, so I'll just do that. What is that? You add sodium hydroxide aqueous, or aqueous sodium hydroxide, aluminum foil, and heat. Okay, and the observation is that gas released. Now, don't say ammonia gas released. Gas released that turns red litmus blue, and that is ammonia. Okay, so if you write ammonia gas released, write the test as well. So ammonia gas released that turns red litmus blue, that is how you know it's ammonia, and the anion is going to be nitrate. Always write the full formula, do not skip the negative part. Yes, Janvi, what's the question? Dry the crystals. Where do I dry the crystals? Oh wait, they asked us to confirm the identity. So the color change should be yellow. I think sodium is gonna be yellow. So where is it? Yeah, so yellow flame will tell me that it is. If it's yellow, then sodium ion. Always write ion for flame test. Okay. Okay. What's happening here? Add drops of aqueous ammonia to solution Q until a change is seen. Green precipitate could be chromium 3, could be iron 2, I don't know. But this is confirming iron 2 because it's not soluble. Okay. Add drops of no wait. You're adding ammonia, so it could be either one of them. I don't know. Crazy cousin, right? So it could be either one of them. Add sodium hydroxide until a change is seen. Again, chromium 3, iron 2, and then add it dissolves. So it is crazy cousin. Chromium is soluble in sodium hydroxide, so this is confirmed chromium 3. Silver nitrate. Silver is used to test for halogen ions. Chloride, bromide, iodide. Okay, so this is going to be chloride because chloride gives white precipitate, bromide gives off-white, and iodide gives yellow precipitate. Okay, add dilute nitric acid to solution Q, then add barium nitrate. With barium nitrate, we are most likely checking for sulfate ion, so white precipitate. Okay, so that is what most likely we are going to get. Wait a minute, I don't know if we're going to get that or not, so why am I writing it? Maybe we don't get anything. Okay, identify the cation in solution Q using the observation. Okay, so cation in solution Q is chromium 3, we've already seen it. See, when I'm already thinking, when I'm reading the question, I don't have to go back to it later on. Okay, so I would advise you to do that. When you're reading it, think and then write your observation. This is your exam paper. You have paid a lot of money for this. Write on the damn thing. Okay, test 3 is incomplete. Describe what else must be done to ensure that white precipitate observed leads to a valid conclusion about anion in solution Q. Okay, so this is white precipitate, it's chloride, it could be sulfate as well. So the only way I know it's not sulfate and it is chloride is that there is no change. Because if there is no change with barium, that means it's making barium chloride, which is soluble, no change seen. But if it was sulfide, then I'll get white precipitate in both of them. Or we don't want that, right? Because silver is used to test for chloride. Describe. Yeah, so we have already mentioned it that. Wait a minute. What else must be done in test 3? What's happening in test 3? Oh, I'll take that back. In chloride, you could also get carbonate. And how do you destroy carbonate? Adding nitric acid. So add nitric acid. Okay. So in test 3 correctly, the observation remains the same. Identify the ion. Because they've said identify, you can write the name, you can write the formula. Both of them are acceptable. Okay. Thank you, Sharia. That's very good. Thank you. No, I'm not ignoring you. Don't worry. I will just read your questions in a bit. The ion identified in 3 is the only anion. Okay, describe the expected observation from test 4. If it is only anion, there will be no change. We already wrote that. Okay, so no change. Okay. Solution Q is acidic. Describe the observation when it is added to sodium carbonate. We will get effervescence, fizzing, bubbles, all of those you can write. So effervescence. Again, you don't lose marks for wrong spelling. It's perfectly fine. Yes, Thunder plays. What's your question? Please ask. Okay, this is something that many students struggle with for some reason. Alright, if you still struggle with it, there is a video on this in the ATP playlist, which has, I think the name is Experimental Design. Watch that, at least half of it, so that you are good with this 6-mark question. Okay, Muntz metal is an alloy that contains zinc and copper. Zinc reacts with sulfuric acid. Copper does not react with sulfuric acid. Why? Because copper is below hydrogen ions. It cannot displace them. It cannot do the reduction of hydrogen ions, so it is unreactive, less reactive. Okay. Plan an investigation to find the percentage by mass of zinc in a powdered sample of Muntz metal. Okay, I want percentage by mass of zinc. That means I want to know how much zinc I have, and I want to know how much mass I had in the beginning. Okay. Okay. So initial mass and mass of zinc. That's what I want to find out. Your plan must include the use of copper. Okay. So here's what I'm going to do. I'm going to take this thing, measure how much metal I have. Then I'm going to add sulfuric acid to that. Zinc is going to react. It's going to dissolve. But copper is not going to react. And copper is going to stay. Afterwards, I'm going to dry it out. Basically take the sulfuric acid out, filter it. The zinc copper that I get, that is the one that is just copper, not zinc. I'm gonna dry it, weigh it, and I will know how much copper I have. I will subtract the copper from the initial mass, and I'll know how much zinc I have. And that zinc divided by the initial mass will give me percentage mass. So that is my thinking process done. Okay. And what will I do all of this in? In a beaker, right? I can just add it, stir it, then filter it, take the residue, dry it, weigh it, then do the formula. Okay, that is my whole process. We need the, I'll get to that in a bit. Okay, all right. So I like to write in points, but again, you're free to write in paragraphs. It's completely fine. Okay, so I'm gonna take a beaker and measure it, its mass, then add Muntz metal in it and measure its mass. Why am I doing this? Because I want to know how much Muntz metal I've added and subtract the beaker's value to figure out exactly the metal. Okay, so metal mass is new value, this mass, or mass into, this is minus beaker mass. Okay, so I know how much metal I have. 3. I'm gonna add sulfuric acid, aqueous sulfuric acid, and stir until no bubbles evolve or stop evolving, because it's going to produce hydrogen gas, so the bubbles are gonna come out. I want to know that all the uh, zinc has reacted, so I should add it in excess so that all the zinc has reacted. Number 4, filter, dry, and weigh the residue. Okay, so now the mass of zinc is gonna be metal mass minus mass in 4. Again, you can call it copper mass or whatever you want to call it. Okay, number 5, percentage of zinc is gonna be mass of zinc divided by metal mass into 100%, and I'm good. That's what I needed to figure out. Again, I've added a little more detail than was required, but I think it's all good. How do I improve this? I repeat and average. That is how I improve this. Okay, so you can do that. Okay, so you can say that repeat all steps and average the results. That's how I can actually improve it. Okay, and what else? I think it's done. I think we have completed it. There's no issue there. Any questions? All right, so this one's done, and we are at the end of this exam paper as well. All right, coming back to your questions, Sharia has explained why we use the non-luminous part. Thank you so much. So apparently that is the blue flame, and it is the one that doesn't have yellow. Obviously, it's the one, if you're looking for yellow flame, then you have to put it in somewhere that's not already yellow. But I guess this is mainly because that's the part that has already, it is where the Bunsen burner is providing the most oxygen, and it's where the fire is in the yellow part. Obviously, as you said, it does not hide the other wire. Okay, Vinny's saying, what's the crazy mnemonic you mentioned? So I said crazy cousin. Okay, and that basically tells me that these things dissolve in sodium hydroxide in excess, and these things dissolve in aqueous ammonia in excess. Okay, so anything else doesn't dissolve, and that is useful in theory paper, but now you're going to get the notes anyway, so you don't really need to remember this. Okay, all right, let's see what other questions you guys have. I'm gonna read the chat now. Can't we do without the formula? What formula are you talking about? Oh, you're talking about the titration formula. It's perfectly fine. I made the titration formula when I was a student. So all my students, I just teach it to them. That's because I honestly did not understand moles. So I just made my own method. Later on, when I became a teacher, I checked with the examiner at Cambridge. They're like, it's perfectly fine. You can use it. Later on, I saw that that method was actually being taught in some schools in China and Singapore. So yeah. Okay. Next question. They didn't tell us about paper 6. Okay, I'm sorry if you did not know. Good luck with the exam tomorrow. Otherwise, good luck with October. Our paper 2 had 3 questions related to organic. Do you think examiner will again test concepts? It doesn't matter what I think. Examiner can or cannot. There's a 50% chance, and it doesn't matter for us. Okay. What are the most important topics for this paper? You've seen 2 papers, right? So notice what topics were there. There was electrolysis. There was rate of reaction. There was salt analysis, there was moles, there was experimental design, of course, and there's others as well, like enthalpy. They did not ask us any question about enthalpy, but they were heating things up. They could have asked. There is redox, even though they did not ask us question about redox, but redox and reactivity Cs, all of that was there. They could have simply asked us, why doesn't copper react and zinc react? So that's reactivity Cs and redox. So it's hard to say which topic is not important. Okay, and of course acid and base as well. Okay, now I'm gonna go to the WhatsApp questions that I've received. Let's see if you guys have sent me any WhatsApp questions. Feel free to send them. Abibi. Okay. All right. Okay, I can't go in the groups. Why have you tagged me in so many questions? The problem with tagging is that you see one and the rest of them you can't see them because they just go away. I'm really sorry, guys. You might have to tag me again. Okay, so there's another student who is saying that they have this. This is another paper. So let me read the question. So what they did was they took a solution F and solid G. Solution F was light green in color with the flame. So light green in color, you go to the flame test notes. I'm loading them. And you see which the light green color is gonna be, and you just note it down right away. Okay, so light green is gonna be copper 2. Oh, sorry, barium ion is light green. Okay, next they're saying that we added sodium hydroxide, aluminum foil, warmed it, and we saw effervescence. That means ammonia gas is coming out, and test is that it should turn red litmus blue. So that is the next part. To the third portion, add 1 centimeter cube of nitric acid followed by silver nitrate, and there is no change. So that means it's not chloride. It doesn't mean anything else. It does not mean it's carbonate. It doesn't mean that it's sulfate. All it means is that there is no chloride. Okay. Identify solution F. So what we have seen is that solution F has barium ion from the flame test. We have seen that it has nitrate ion because of the ammonia gas. So it's barium nitrate. Now, write the formula correctly. So the barium nitrate formula is Ba plus 2 NO3 negative 1 combining to give you BaNO3 2. Write this. If you can't write that, write the name, but don't write wrong formula. Okay. State what would be observed if the student adds sulfuric acid to another portion of solution F. Sorry, it's dilute sulfuric acid to another portion of solution F. So you had barium nitrate and you're adding sulfuric acid. Barium is going to test for sulfate, right? So barium sulfate produces white precipitate. So you're going to see white precipitate. That is the answer to that. Now notice that examiner usually what does it do? In your notes, what does it say? It says, for example, for sulfate ion, it says to test for sulfate ion, acidify with dilute nitric acid because you're destroying carbonates. Add barium nitrate. Now you already have barium and you're adding sulfuric acid. You're adding sulfate yourself and you already have barium. So he has flipped the narrative, but it doesn't matter. You're still getting barium, you're still getting sulfate. You react them together, you're gonna get white precipitate. Okay. Can I suggest any tips for A star? Honestly, I don't know. I don't know how to answer that. Okay, next. I don't know how to solve titration question right now. I would suggest go through the 2 titration questions that we saw today. And if you really want to go through any moles, there's again ATP moles worksheet that I've solved in the video. Okay, so it's again, I think it's ATP1 or ATP2 video in the playlist. Watch like 15 minutes of that. Do not do topicals at this time. Don't do that. Okay. Watch Carboxyl. Yeah, it's a really good channel. Watch that. This is for O levels and IGCSE. We have a paper 4 tomorrow. You scored 32 out of 40. That is actually good. As long as you're scoring like 30 plus, you're good. Don't worry. Acidify with nitric acid, not acidify with nitrate. Okay, so I guess this is it for today. And thank you so much, guys. It was wonderful having you again here. And I would love to do another session for AS. I think we have an exam coming up on, I'll have to check the date sheet. But yeah, I'll see you for AS next time. And yeah, take care. All the very best for the exam. और अब सो जाओ. Alright, bye.